So before we get too heavily into valence bonding theory, we've laid out all the steps we need to sort of take a look at how valence bonding theory works. And we've been doing a lot of the idea necessary for valence bonding theory. But it doesn't really describe how atoms bind. At the moment we've been talking about just the practicalities. We can predict structures. We can tell whether something is polar or not. But valence bonding theory actually talks about the mechanics of how the atoms bind together. And for this, though, we should probably just discuss the electronic structure of atoms, just as a quick review. If you remember, you have your stereotypical hydrogen atom. That hydrogen atom has electrons in the 1s subshell, and in this case it has one electron in the 1s subshell. And if you have another hydrogen over here, it also has its electron in the 1s subshell. And valence bonding theory basically says, well, electrons in a molecule occupy the same atomic orbitals as the individual atoms. So basically, it behaves as if the atoms are distinct. And so they each have their individual orbitals. If you remember what an s orbital looks like, it's sort of this round shape. And so here we have our two hydrogens. And they each have their unpaired electron in it. And those electrons match spins or pair. And they end up pairing up to generate a new bond with a shared pair of electrons between the two hydrogens. So this is our valence bonding approach. It all deals with the unpaired electrons in the valence shell. This is what we were doing with our Lewis dot structures. So if we take some generic chlorine, and it has its 7 valence electrons, and you have a hydrogen with its one unpaired electron, those two can come together. A more simplistic picture would be that the electrons in the 3s in this case, 3s and 3p subshell, if we take a look at the chlorine, the electrons, there would be an unoccupied p orbital. If you remember what a p orbital looks like, it sort of has this lobe shape with the central atom in the middle. The unpaired electron would sit in there, and it could interact with the 1s orbital of the hydrogen to form the HCl molecule with the shared pair of electrons taking place between the two atoms. And we could do something similar. Notice we have these 3 sets of non-interacting electrons. Those would correspond to the 3 lone pairs on the chlorine. And so there's good agreement with this. This model seems to work fairly well even for more complex structures. Again, we've already been doing this. We've been working under the assumption that chlorine can form at most 1 bond. Oxygen typically forms 2 bonds, etc., based on the number of missing valence electrons. And so oxygen, again, we have the same idea as a 2s, 2p. If we take a look at the oxygen, one set of, and we see that we have 2 unpaired electrons in the p orbitals, and if we look at our oxygen atom, we could imagine those electrons residing in these p orbitals, where this is one p orbital, this is the other, and along would come a hydrogen with its unpaired electron, another hydrogen with its unpaired electron, and you'd end up forming a water molecule out. And it approximates the shape even of the molecules that we were talking about. But there's some difficulties with this approximation. For instance, if you actually look at the bond angles in that oxygen, and so we see that the if we take a look at the orbitals that make up the oxygen, we see that they are orthogonal to one another, they're right angles to one another. And this means that that shape would define them at perpendicular to one another. And so the bond angle should be 90 degrees, and that's not what we see. Additionally, there are some other idiosyncrasies with this. If we take a look at something like carbon, look at its electronic configuration, it's 2s, 2p, we see that carbon has 4 valence electrons, and if we use the valence bonding model, we should only worry about the unpaired electrons, and so carbon typically would only form 2 bonds. But that's not what we see. We all know that carbon forms 4 bonds. So the valence bonding model needs to be modified, and the way it's modified deals with hybrids. So rather than talking about the atomic orbitals on the atom as discrete entities, we start to change them and mix them to make what we call the hybrid orbitals. Now, hybrid orbitals are a linear combination of molecular orbitals. So you take 2 orbitals, such as an s orbital and a p orbital, and you mathematically combine them. You have to remember that the p orbital has a mixed phase. And so you combine them, and whenever you bring in 2 orbitals, this is the secret to a lot of orbital math, 2 orbitals in means 2 orbitals out. That means you get 2 different combinations of orbitals that look pretty similar, but actually have slightly different, what they have at different geometries, different angles. And they actually point, in this case, at away from one another. So you end up bringing in 2 orbitals, you get out 2 orbitals. So let's take a look at what these hybrids, we bring in 1 s orbital and 1 p orbital, and you bring them together, and you get this multi-lobe system with the bulk of the density pointing away from the atom. So if you overlap these 2 structures, what we see is a central atom that then has 2 lobes of bonding. Now, if you do this, again, this is an sp orbital, 1s, 1p. If you take an s and 2 p's, an s and a p and another p, and you combine them, you get 3 new orbitals that, again, are all distributed at 120 degrees from one another. Notice what I just said. We had one that was distributed at 180 degrees, and now we have another that's distributed at 120 degrees from one another. And if you make another hybrid that involves an s, a p, and a d, an s, a p, and a p, and a p, or 3 p's and 1 s, that becomes an sp3 orbital. Generates 4 new sp3 orbitals. Now, the angles between these are 109.5 degrees. Now, if you've been paying attention at all, you'll know that these numbers have come up before. You can combine an s orbital and a p to generate 2 new sp hybrids. And on paper, take the s orbital and a p orbital from a molecule, and we combine two of them, and this gets transformed into one of them gets raised a little in energy, one of them gets lowered a little in energy, and so this leaves us with our two sp hybrids and two p orbitals. And the sp hybrids are degenerate. They're all the same energy, where the p are slightly elevated. Now you can also do the same for the s, the p, and the p to generate the sp2 hybrids. These would sort of jut off into space. I'm going to leave out the other lobe. 120 degrees between them. Sorry, 180 degrees between them. And you can do the same thing with an sp2 hybrid. They jet off into space. But the angles between them at 120 degrees. Electronically, these would look sort of like this, where we have the p orbital, we have our sp2 orbitals, the three of them. And then we also have the one where we combine the s and a bunch of p's to generate the sp3 orbitals, which then would take these four. So you can do the same thing with the s and the p to generate the sp3 hybrids, which would generate four equal orbitals that jet off into space at 109.5 degrees to generate a tetrahedron. So these shapes are starting to mimic those shapes of the structures that we've already seen. And it works the same, it works backwards and forwards. If something has 109.5 degree angles, chances are good that it is generated from sp3 hybridized. So even if we don't know that it's sp3 hybridized at the start, by looking at its geometry, we can say that it's sp3. So the geometry tells us the hybridization, and the hybridization tells us the geometry. And we don't even need, we can actually use just Lewis dot structures to tell us the geometry and therefore the hybridization. So what do I mean by this? So if we take a look at our example of nitrate, NO3, we draw the nitrate, we can look at the nitrogen and we can say, oh, this nitrogen, because of the bond angles of being 120 degrees, must be generated from an sp2 hybridized structures. So this is this nitrogen has an sp2 hybrid. The oxygens would be sp3 hybridized because it has 4 electron regions and therefore it has to be tetrahedral geometry, whereas this oxygen would be sp2 hybridized. Now, there are two other hybrids. The dsp3 and d2sp3 that generate 5 degenerate orbitals. Because they are made up of 5 individual orbitals combined to find 5 new hybrids, and the one that generates 6 new hybrids. And they're all the same in energy, and these correspond to our trigonal bipyramidal and our octahedral geometries. And so if you see something with an octahedral geometry, you know that it is dsp3 hybridized.